So now, having studied quite a lot about correlated equilibria, much actually more than we need to talk about what Raufgarten did, let's now just look about another definition of a correlated equilibria, so that we'll use exactly the same definition as Raufgarten used in his paper about efficiency or smoothness approach. So we finish this with this statement about identifying status outcomes. That every finite game, in every finite game, every distribution which is obtainable by correlated equilibrium over the outcomes can also be obtained by correlated equilibrium where the states of this space are S. So basically, that you look only at which your strategy profile do we get randomly, and then for each player I, the player just knows what is the player knows what his strategy in the randomly drawn profile is. So for each of the possible strategies of that player I, all those who are the same are for me the same information set. So that's quite a natural way of, I think, of identifying states, of to think about correlated equilibria. So basically, this randomization goes like that. According to some random distribution, one of the states of the game, one of the pure states, is basically drawn, and that sample, which is a pure state, then is divulged to each player, but not the whole sample. You are only told about what is your role. I being this mediator, I randomly take this state according to some distribution. Then I tell player I, you should do that. Player J, you should do that, and so on. I mean, player 1, 2, and so on. To the player, to the player. And then, given this knowledge, it's optimal for you to play with. So we may confine our attention to such correlated equilibria. And now, using this approach, and I want to arrive at another definition of correlated equilibria, which is going to be much, much more intuitive. That's going to be the main takeaway from this lecture. So, given a game, something is a correlated equilibrium, if and only if recall the observation. The correlated equilibrium, or the something that some profile is not worse than any other profile if someone deviates, and you look at just the weighted sum as what you get from a profile. Here you can, one of the other options is to tell that something is a correlated equilibrium if and only if for every event which belongs to an information set, which has a positive probability, conditioning on the information set of this event from the point of view of player I, what player gets by playing what she plays according to these SI strategies is at least what she would get if she deviates. So conditioning on this event, on this sample, it's always best for player I to play what she should play according to the group. This conditional expected value. Now, this uses actually the following equivalent definition. This observation uses the following equivalent definition. Given a game, now think about only concentrating on the equilibria of the form we just told that the omega is the state of the game, and the players, the information of the player knows what is her strategy in the drawn strategy profile. Then, given a game, a joint distribution is a correlated equilibrium if and only if. So I look what happens if this is made according to this case when omega is the state of the game. And then I get from this observation that this one is the following. The joint distribution of the correlated equilibrium only for any player and for any strategy of that player Si and another strategy Si prime, such that the probability of Si is positive, it's best for the player to play what she has to play, then to deviate, conditioned by on Si. That's exactly this characterization of the coarse correlated equilibria when I only constrain myself to the equilibria where omega is S, the set of states of the game, and the information set are. So again, the main takeaway is that an equilibrium proper is a coarse correlated equilibrium if for any two pure for any player and for any two pure strat player, one of which has a positive probability, otherwise there is no reason to condition that strategy. It's not defined and it's not interesting. But when one has a positive probability, then condition that player I plays I as I, it's best for player I to play that indeed. Then, I mean, conditioned on player I being, told to play as I, according to this S has been drawn. Condition that he's being told to play as I, it's indeed best for him to play as I. Condition what you are told to play as I, it's best for you to indeed play as I. That's the idea of the correlated equilibrium. So we guard against all the possible deviations. When you know that you are told as I, what are the possible deviations, and it's never good for you to deviate. That's the definition. And this can be interpreted, as I have said already, that you have a mediated play. A mediated draws some strategy profiles according to some probability distribution, which is this equilibrium, and privately tells player I, you should play as I. Every player is told what is her role, what is her strategy in the drawn profile. And then, following this recommendation is indeed optimal. When everyone else follows the recommendation and you condition on this recommendation. And as I said in the beginning, one of the important advantages of this equilibria is that unlike the mixed, unlike the pure equilibria, those can be found in polynomial. Of course, they're not empty because the mixed also are not empty. They also can be computed in polynomial time and easily learned by some natural dynamics, none of which I'm going now to show you now, but that's something which is you may take a look in the book, for example, if you are curious and have time. Now the next topic is coarse correlated equilibrium. They are less maybe famous, but still important. And as I said, they're going to play a role in what Raufgarten does. So here we're going to make another definition, and that definition by following work by Nubin and Viol. Given again, a joint distribution of outcomes, of a few outcomes, is a coarse correlated equilibrium if for any player and for any possible deviation, again, you're talking about pure deviations, but it's enough because linearity, about pure deviations, it's never good for you to deviate. So the difference from the definition of a coarse correlated equilibrium, that here in the coarse correlated, we condition on what you are told. And here we don't condition on what you are told, because you're not told anything. So this definition, coarse correlated equilibrium, requires there is no profitable unilateral deviation when players are unaware. This definition, not definitions. This definition. So when players unaware of any of what is this S drawn by sigma, it's best for you to play what you play. Here on the other hand, so here we guard against only those unaware definitions, deviation, while the correlated equilibrium also tells that it's never good for us to deviate even if we know this sigma si. So this is a stronger requirement, and therefore there are generally speaking less correlated equilibria than coarse correlated. So the correlated in general are included in the coarse correlated. And since we already know that correlated include the mixed, that we know this inclusion chain. That the pure are included in the mix. Of course, when we identify the pure with the mixed, we just place that pure with probability 1 and the rest is probability 0. The mixed, in the sense we just described in this lecture, are included in the correlated, and the correlated are included in the coarse correlated. And of course, therefore, correlated are even easier, or at least not harder than coarse correlated to find computationally or to learn. And indeed, there is, I think, an easier learning approach for those, but this is beyond our scope. I don't remember the exact learning results, but I think that there is even a better learning way to those coarse correlated. So those inclusions are generally strict, as we now demonstrate. So we now find an example, show a simple example, natural example, where all those inclusions are strict. So consider a conjunction game with resources from 0 to 5. 4 players, we start the set, which in this case are not just subsets, but the subsets are just singletons. So the strategy of player is taking one of those edges. You can think of that as indeed some routine when you just choose one of those edges. Maybe those are all parallel edges, and you can choose any of those parallel edges. Every player chooses any of those parallel edges. But that's a general thing, but we can think of that as this routing game, atomic routing, I mean. As one, defining the lot of an edge by the number of players who use that edge. Again, the size is 1. It's just the number of players who use the edge, and the costs of the edge are given by some function, which in this case, let's look at that as the identity. And the cost of a profile is just the sum of the costs of all those players, which by changing the order of summation is exactly equal to, excuse me, the cost of a player is, the cost of a player is the sum of the cost of the edges the player uses. So these are the edges the player uses, and these are the cost of the edges the player uses. So this is the game, a very concrete, simple game. Here, the next equilibria are the 6, choose 4. So I choose all the possibilities to start of size 4 from the types of 6 edges. When I choose exactly 4 different distinct edges, because I don't want to choose the same edge as someone else uses, I can always improve by choosing a non-used edge. So the equilibria are all those profiles, and the cost in those equilibria are all 1. Because the load of your edge is 1. Nobody interferes, nobody. Now, there is, however, a mixed equilibrium, which is not a pure equilibrium. For example, look just at the uniform distribution. Every player uniformly chooses each of the edges. Probability 1 over the number of edges, of course. In this case, the number of edges is 6. And that's going to cost a bit more. The social cost is going to be okay. I apologize, it's not cost is not a social cost is one, but rather the cost of each player is one. I think I'm not mistaken. Let me make sure I'm not mistaken. Let me make sure from the paper I'm not mistaken. Yes. Yes, exactly. I'm not mistaken, it was just type. Every player, it was not the social cost, it's just what every player incurs. That's a bet. How much every player bet. So it's going to be CI for every player I. And it's going to be CI also for every player I. So I need to do it like this. So this is going to be CI for every player I, and also this is going to be CI for every player. Now, so we have already shown that Nash are strictly in equilibrium. The next, we need to find what is this reversal of what we have said. Consider all the outcomes. See, I for every player I, this is CI. Consider all the outcomes. Now I'm going to show you a mixed, coarse correlated, which is not mixed. So consider all the outcomes with one resource as two players and two other resources. There are not all the resources are used. Two other are chosen by one player each. So only three resources are used. This outcome. First of all, this so consider all such outcomes, and then you uniformly choose all such outcomes. And I claim this is a C which is not mixed. It's correlated but not mixed. Why? First of all, it's not a product distribution, because what you do is dependent on what the others do. So you want there is one resource with two players and two others with one player each. So you may not go to some resources which are just some resources that you have exactly requirements what to do depending on what the other players do. So it's not a product distribution. It's not mixed Nash equilibrium. Why is it a correlated one? Because in the definition of a correlated equilibrium, both sides, what is going to be your expected utility conditioned on what you are told when you don't deviate, and what's going to be that when you do deviate, conditioned on what you are told. It can be shown to be always 3 over 2. You just can calculate. So it's weakly never better for you to deviate. It's a correlated equilibrium. Next, finally, we want to show that there is something which is coarse correlated and not correlated. So finally, consider the outcomes. Your outcomes where the chosen resources are either 0 to 4, all the resources with the odd numbers, or all the resources with the even number. Oh, okay, the other way around. Either all the even resources 0, 2, and 4, or all the odd resources 1, 3, and 5. Now consider then the uniform distribution over all such outcomes, and then I claim it's coarse correlated but not correlated. Why? It's not a correlated equilibrium because deviating, again, you can look at the details, but deviating from resource I to resource I plus 1 is always strictly profitable. One, clearly. If you're using resource I, it means that I plus 1 has another parity, modulo 60. And then it's going to be strictly profitable to use something which is not used by anyone. Now, it's still coarse correlated because both sides in this condition for being coarse correlated, that it's never better for you to deviate without any condition. Now, but if we to deviate, both sides are always, again, we can check this, equal to 3 over 2. So it's weakly optimum flavor. Okay, so we have seen this example, so that those inclusions can be strict, and that's the end of this lecture. Well, let's just recap. So the wrapping up is that we looked at the extensions of Nash equilibria, mixed Nash, which include Nash in the sense we described, so that we can generate a sentiment and distribution, and coarse correlated equilibria, which include, mixed Nash include Nash in the sense we know, in the sense that we describe, and indeed we identify that you are strategies, which the mixed strategies that have the that play those pure with probability 1. Coarse correlated include mix with in the sense we described. That this distribution basically the coarse correlated induces this distribution of a mix. And then we also prove that the coarse correlated pairs extend the Nash equilibrium pairs in a convex manner. So if you have some pairs of a convex or of coarse correlated equilibria, then any convex combination is going to be also a pair of some correlated equilibrium, but they can go beyond the convex span of mixed Nash equilibrium. And we look at several equivalent definitions. I said one of which we are going to use in the next lecture, which is the most important for us. And then coarse correlated equilibria. Those are even broader than correlated. They also extend the correlated in the sense we described. They just extend the correlated because they are those distributions. They extend the correlated anyway. And the inclusions of this Nash in mixed in correlated, and correlated in coarse correlated, all of them can be strict even in one example. Now, we discovered the most useful probabilistic extensions. Of course, there are many other kinds of solutions, strong equilibrium, that. So we have not covered all of them. Of course, there are infinitely many possibilities. So just make sure you, if you do want to understand those approach to what can be played in the game, of course, you have infinitely many possibilities and just a lot of classical solutions. Good. So now let's move to the final, the generalization of many things we have seen in the work of Garden.